In this video, we solve problem 14.7.042 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to convert the integral from rectangular coordinates to both cylindrical and spherical coordinates. And this is what their answer looks like on WebAssign. So first we're asked to convert, and they set this up for us. So we're told that the lower bounds for z, r, and theta are all 0. And we just need to find the upper bounds. We also need to find the new integrand. And then in spherical coordinates, we actually have a sum of two integrals. They want us to use the order of integration d rho, d phi, d theta. And for this first integral, we want all three variables to start at 0. And for the second integral, we see that phi starts at pi over 6. And then it says evaluate the simplest iterated integral. So that's the plan. Just to get us started, here's the idea. Anytime you're converting an integral from one coordinate system to another, let's say we have a triple integral over q of some function times dv there. The bounds here describe the region that you're integrating over. This region q is a solid region in three-dimensional space. If I want to convert this to some other coordinate system, I'll go from Q to, say, another solid region, I'll call it D. And then we want this integrand to be replaced. Well, actually, I guess that's not going to have a star by it. We're going to have the new integrand here. And this is going to be in terms of the new variables. And then we want the dv in terms of the new variables. So basically, you need three things. You need the new bounds. So we're going to need bounds for r, theta, and z when we are in cylindrical coordinates, or rho, theta, and phi when we're in spherical coordinates. Then we want this function in terms of the new variables. So we'll take this integrand and write it in terms of the new variables. So I'll say it's a conversion of the integrand. And then we want dv in terms of the new variables. Now, dv is not just d rho d phi d theta or dz d r d theta. It just really depends on which coordinate system you're switching to. Often there's an extra factor here that comes from the Jacobian that takes you from the variables x, y, and z to the three new variables. So with that in mind, what I always recommend you do with a problem like this, anytime you're trying to convert from one coordinate system to another, is to start with the bounds first. And in order to get the bounds, the easiest way to start is to graph the region. So remember how this works. The innermost bounds go with the innermost variable. So these tell me that the variable z is between 0 and the square root of 16 minus x squared minus y squared. Okay, and then the next set of bounds goes with that next variable. You're sort of going on the inside and then you're working your way out. This tells me that y starts at 0 and ends at the square root of 4 minus x squared. And then the last bounds go with that outermost variable. So x goes from 0 to 2. So you can think of these as 6 surfaces if you want to. Z equals 0 is a plane. Z equals this square root is a different surface. Y equals 0 is a plane. Y equals this square root is a particular surface. It's called a cylinder because it doesn't have any z's in it. And then this is the plane x equals 0 and x equals 2. So we want to think about the region in three-dimensional space that is bounded by all 6 of those surfaces. And I usually just start with the bounds for z, and then I work my way out. So if we want to go to rectangular, excuse me, not rectangular, from rectangular to cylindrical coordinates, I think it's easiest to start with z and write that in terms of r and theta. So we have z goes from 0 to this square root. Now, remember in cylindrical coordinates, we have x squared plus y squared equals r squared. So as soon as I see that x squared or negative x squared minus y squared, I think if I factor out a negative, then I'll have that, which is nice. And then I can replace x squared plus y squared with r squared because we're in cylindrical coordinates. So I'm just substituting r squared for x squared plus y squared. So these are our bounds for z, which is nice. Now that we have those bounds for z, that's enough to kind of get started over here. Z is going to go from 0 to the square root of 16 minus r squared. But if I want the bounds for r and theta, I really need to graph the whole region. So let's graph it. Z equals 0. We know that's the xy plane. So that down here. Z equals 0 is down here. Up 1 unit would be another plane parallel to that above the xy plane. 2 units up, we'd have z equals 2. That's all of those planes that are parallel to the xy plane are z equals a constant. So z equals 0 is the xy plane itself. And then for this one, z equals the positive square root of 16 minus x squared minus y squared. What I would recommend is rearranging that equation. I don't have square root functions like this memorized. I don't know what those graphs necessarily look like off the top of my head. But I noticed the x squared and y squared. So I'm thinking, let's get rid of the square root by squaring both sides and see if we can't make this look like one of our quadric surfaces. So we've got z squared equals 16 minus x squared minus y squared. And if you add x squared and y squared to both sides, you get x squared plus y squared plus z squared equals 16. Since we're not subtracting anything from the x, y, or z, this is a sphere centered at the origin. And the radius squared is 16. So the radius is the square root of 16, or 4. And we actually don't get the whole sphere because this says that z is the positive square root. Z is between the xy plane and the positive square root of that quantity. So that just means that as I go from this line to this line, these aren't equivalent unless I add this extra restriction. Z has to be greater than or equal to 0 because z was a positive square root of some quantity. So that means it's not a sphere, it's not the whole sphere, it's the top half of the sphere. It's a hemisphere. Okay, and it's got a radius of 4. So we're going to go left 4 and right 4 and back 4 and forward 4 and then up 4. This is not to scale. And we're trying to draw it with a little bit of perspective, so it's not going to be perfect. It's not going to be perfectly circular because we're thinking of seeing this on some angle. But that might be our hemisphere. Okay, so z starts at the xy plane and goes to this. So you might think, well, maybe spherical coordinates is the way to go because you're dealing with part of the sphere here. But that's not the whole picture. That's just based on the bounds for z. To figure out what our solid region looks like, we also need to look at the bounds for y and x. So this is what I have here. I have y equals 0 is one bound, and y equals the square root of 4 minus x squared is another bound. Let's think about where y equals 0 is. Y equals 4 is here, y equals 3 is there, y equals 2 is there, 1, and then 0 would be right here. So this plane containing that positive z-axis, that's y equals 0. So it's the plane that is intersecting that sphere along sort of this seam. y equals 0 is the same as the xz plane, and I hope that you can see that. Like part of the sphere is on the other side of the plane and the other part of the sphere is sort of close to us. And then you might say, okay, well, what about the rest of it? Y equals this positive square root of 4 minus x squared. Well, we can handle that by just rearranging that equation. Again, when we have an x squared under a radical, we might not know off the top of our head what that looks like. It's not one of our functions that we studied in pre-calculus or college algebra. It's not one of those that we memorized because of that x squared under the radical. So we might square both sides and then try to rearrange the equation. Remember, y was a positive square root, so that means y has to be greater than or equal to 0. And that means we get that. And if we add x squared to both sides, we see x squared plus y squared equals 4. We have this restriction that y is greater than or equal to 0. Now that's a circle centered at the origin. With a radius of the square root of 4. The radius squared is 4, so the radius is the square root of 4, which is 2. So in the xy plane, we're told that y starts at 0 and goes to that positive square root. You know, y equals 0 is right here in the xy plane. That's the x-axis. And then y equals the positive square root is the top half of this circle. So we'll have a circle that looks like this, and it has a radius of 2. Okay, so y goes from here to here, and then we're told that x goes from 0 to 2. So we actually don't get the entire region. We just get the part of the region between this function and this function where x is between 0 and 2. So we're talking about that region right there. So when I go over here and I look at my graph in 3-dimensional space, I see I'm talking about the part of this hemisphere, or part of this, part of a sphere, I guess, that is above this little circular sector in the xy plane. Now, one thing I want you to notice is that the radius of the sphere centered at the origin that's described here is 4, and the radius of this circle is 2. So when I look at this region in the xy plane, what I'm going to see is this. Here, x and y range from 4 to 4, or x goes from 0 to 4, y goes from 0 to 4 here. But with this region, x and y go from 0 to 2, but it's not that rectangle, it's bounded by that curve. So we have this. So you might say to yourself, okay, well, what does that mean for our solid region? Well, the solid region is the region between this sphere and the xy plane above this little piece. So you might sort of draw lines going up. You can think of x squared plus y squared equals 4 as being a cylinder. You're going to see part of that cylinder over here. And then we're going to have a little part of the sphere sitting on top of that. It's like a spherical cap right there. So that is our solid region, the blue region that I just tried to draw. Okay, so if we're going to spherical coordinates, we need bounds for z. Converting these equations was relatively easy. We said that z equals 0 is still the lower bound. Z equals the positive square root of 16 minus x squared minus y squared is the upper bound. And that can be written this way in cylindrical coordinates. And then to find the bounds for r and theta, we always look at the projection of this solid region onto the xy plane. And then we use that image to help us come up with the bounds for r and theta. R equals 0 is just a single point. R equals 1 is a circle of radius 1. R equals 2 is a circle of radius 2, and so on. So remember, R is distance from the origin in the xy plane. So R is going from 0 out to 2. You want to think of these as circles sort of radiating out. Now you would have the entire disk if there was no restriction on theta. If theta could be anything, or if theta went from 0 to 2 pi. But we do have a restriction on theta. We don't have the entire disk. Theta is an angle that sweeps around the xy plane. So we're going to think of theta as starting right here and ending right here. Here, theta is 0, or that's one version of it. You could say theta is 0 radians there. And over here, if I'm just going from here to here, and I'm not going around multiple times, I'm just going once, then we have theta equals pi over 2. So theta goes from 0 to pi over 2. So those are our bounds for r and theta. These are our bounds for z. And we can fill these in up here. So r goes from 0 to 2. Theta goes from 0 to pi over 2. And now we just need a new integrand. Well, to find the new integrand, we need to make a replacement. We need to find the original integrand in terms of r, theta, and z. And we also need to substitute the dv. Remember how that works. Our f was originally the square root of x squared plus y squared. And if you wanted, you could substitute x equals r cosine of theta and y equals r sine of theta. That's one way of doing it. Because we know that that's what x and y are equal to when you are in polar coordinates. Or you could just remember that x squared plus y squared equals r squared. Now, if we square each of these factors separately, and then we factor out the r squared, we see that cosine squared plus sine squared, and we know that that's got to be 1. This is the square root of r squared, and the square root of r squared is r. So you could have skipped all of that if you remembered that x squared plus y squared is equal to r squared in cylindrical coordinates or polar coordinates. Or if you prefer, you can always just substitute, and the substitution and simplification will lead you to the same place. So that's our f, that's our new integrand, and then dv is not dr, dz, d theta, or some other order. It's r times dz, dr, d theta. And we can change the order of multiplication if we want, because multiplication is commutative when we're talking about real numbers. Okay, so that's our new f, that's our new dv. When you put those two pieces together, we have the triple integral over the region Q of f, which is given by r, times dv, which is r, dz, dr, d theta. And of course, you could simplify that. R times r is going to be an r squared. And you should have the appropriate bounds, which we've already talked about. So z goes from 0 to the square root of 16 minus r squared, which is the equation of that hemisphere. Then r goes from 0 to 2. That's from this image. And then theta starts at 0, and it's like an angle that sweeps. It starts at 0 and it sweeps through pi over 2. It goes from there to there. If I put my pen at the origin, it goes from there to there. And then our new integrand was r times that r from the dv, so we have r squared. All right, so we're going to do the same thing with spherical coordinates. We've got a little bit of a hint here. They're telling us that in spherical coordinates, you have to write it as the sum of two integrals. So you might think, how will I do that? Well, I think the issue here is the range of values for phi, because remember what phi equals a constant tells us. Just as a brief review, if phi is equal to 0, phi is an angle that we're making with the positive z-axis. then we would just end up with this z-axis right here. Now, if phi is equal to, say, pi over 6, or just some constant, and that constant is between zero and pi over 2, what we get is a cone. And as long as we're talking about values of phi between 0 and pi over 2, that cone is going to face up. So you have something that looks like that. Because we're assuming when we say phi is a constant that there's some other assumptions here. We're saying that rho, that is the distance from the origin, is free to be anything. And we're also assuming that theta is free to be anything. It's just kind of like when you say that if y equals 2 and you're talking about an equation, you draw that line because y is equal to 2, but x can be any value, and so we get the whole line. In the same way, if rho, that's the distance from the origin, can be any value, and theta is free, so that angle that we're making with a positive x-axis can be any value. But this angle phi is a constant. That's an angle measured from the x-axis, or sorry, from the z-axis to some line. Well, there are infinitely many ways that could happen. I always think of like a little snow cone cup. If you look around that line of symmetry, phi is the angle from that line of symmetry in the middle of your snow cone cup out to the edge of that little cup. And it doesn't matter which direction you go, really, that's going to be the same phi as that one. And it's going to be the same phi or the same angle that you would make if you went from the z-axis to the other edge, just because of the nature of the symmetry. So phi equals 0 looks like this. Phi equals a constant between 0 and pi over 2 looks like that. If phi equals pi over 2, that's the xy plane. Another way of saying that would just to say that z is equal to 0. And then if phi is a constant between pi over 2 and pi, then we just have a cone that faces down, because we make an angle like this, and then we say that theta and rho are free to be anything. And if phi is equal to pi, we would get the z-axis, the negative z-axis. Okay, so with that in mind, looking at this picture, well, we're going to have a different boundary for rho when we're inside this cone as opposed to when we're outside the cone. Because when we're inside the cone, rho is going from 0 out to that top part of the sphere. But when we're outside the cone, rho is going from 0 to this cylinder that has equation x squared plus y squared equals 4. So it's a little bit difficult, or it might be initially a little bit difficult to figure out how we get the bounds there. But I think it's really helpful to remember what rho equals a constant means. That's a sphere of radius rho. Phi equals a constant means a cone generally, except for those special cases. And theta equals a constant is a plane that intersects the x-axis or intersects the z-axis at a certain angle from the x-axis. But that's beside the point here. So what I would recommend that we do is split this into two pieces. First, we will talk about describing that solid region that looks kind of like a snow cone. It's above this cone here. Again, rho starts at 0 because rho equals 0 is the origin, and it goes out to that equation of the sphere. And remember from our coordinate conversion formulas that x squared plus y squared plus z squared equals rho squared. So when we're converting, x squared plus y squared plus z squared equals 16, we can change that to rho squared equals 16. So that's rho equals, just take that positive square root of both sides. So rho equals 4. And that means our bounds for rho should be 0 to 4 when we're inside that little cone. And then you might say, okay, what about our bounds for phi? Well, phi equals 0 is included inside that cone. If you look at it, we start here on the z-axis, and then we go out to like an edge that looks like that. And if you're trying to figure out what that edge is that looks like that, like what is the value of phi that gives us that cone, one way we can do it is we can think about the value of z, where this cylinder, x squared plus y squared equals 4, meets the sphere, x squared plus y squared plus z squared equals 16. So that will get us z, and then once we have z, we can find phi because of the relationship between phi and z. So we know x squared plus y squared is equal to 4 on that seam of intersection, and x squared plus y squared plus z squared is equal to 16. That's on our sphere at the seam of intersection. So I can take this x squared plus y squared and I can replace it with 4, which means z squared equals 12, and z is then the positive square root of 12. Square root of 12 is the square root of 4 times 3. Square root of 4 is 2. Square root of 3 can't be simplified, so we usually leave it under the radical. This still does not get us phi. We know already that phi starts at 0 because the z-axis is included. But you might say, how do I get that upper bound? Well, we can use this fact. Remember, z is equal to rho times cosine of phi. Now I know that z is equal to 2 times the square root of 3 on that line of intersection. I say line, I mean curve of intersection right here. I know what z is, and I also know that rho is equal to 4 because we're on that sphere as well. So there's only one variable here, and that's phi. So we have z equals 2 times the square root of 3, rho equals 4, and that gets us that. And then if we subtract, or excuse me, if we divide both sides by 4, we get that. That simplifies to square root of 3 over 2. And then that means that phi is, well, satisfies this relationship. Cosine of phi is square root of 3 over 2. So that means the adjacent side is square root of 3 when the hypotenuse is 2. And that's a 1, 2 square root of 3 triangle. The opposite the 1 in a 1, 2 square root of 3 triangle is a 30-degree angle. And 30 degrees is 1/6 of 180 degrees, and 180 degrees is pi radians. So this is a 1/6 of pi. We always need to be in radians when we're in calculus class rather than in degrees, even though we still think in degrees. At least I still think in degrees. Okay, so inside our cone, phi goes from 0 to pi over 6, and rho goes from 0 to 4 because we're going from the origin out to that sphere. Now, if you want to find bounds for theta, you use the same bounds for theta that you would have used in polar coordinates. So we're still looking at this. So theta starts at 0 and goes to pi over 2. So we're still going to use the same bounds there. Oops, there we go. So we've got these bounds, and these bounds. Excuse me, I'm like slurping my coffee over here. It's a little gross. Sorry about that. So those are our first set of bounds. We also need an integrand, and we'll do that in a little bit. So we said rho goes from 0 to 4, phi goes from 0 to pi over 6, and theta goes from 0 to pi over 2. Okay, now you might say, well, what are the bounds for phi now? And what are the bounds for rho now? And what are the bounds for theta now? Well, I don't think theta is going to change, because when we're talking about the rest of our solid region, we're talking about the region between this sort of part of a snow cone that we're imagining back here in that corner, and the cylinder. So phi is starting at the cone and it's going to the xy plane. With that in mind, I think we can see that phi is starting at pi over 6 and it's going to pi over 2. So those are our bounds for phi. Similarly for theta, we're still starting on the x-axis and going to the y-axis, or like this, if we look at it with this orientation. So theta is starting at 0 and going to pi over 2. Then the only question becomes, what are the bounds for rho? I'm not going from one point out to a sphere. This time I'm going from a point out to a cylinder. And that cylinder has equation x squared plus y squared equals 4. That's okay. We can convert this equation involving x squared plus y squared equals 4 into an equation involving rho using our coordinate conversion formulas. So we'll do that. So we have phi between pi over 6 and pi over 2. Again, because we're starting on the cone and going to the xy plane. Remember, the xy plane has equation e equals pi over 2. This one should be pi over 6, sorry. Going from there to there. Theta is still going this way from 0 to pi over 2. And we know that rho starts at 0 because we include the origin. Our question is, what is that other bound? The other bound is given by, or needs to describe, that cylinder with the equation x squared plus y squared equals 4. So we just substitute. Remember, in spherical coordinates, x is equal to rho sine of phi times cosine of theta, and y is equal to rho sine of phi times sine of theta. We want to square those and add them together, set that equal to 4, and then solve for phi, solve for rho, because that'll be our upper bound here. So in order to do that, just rewrite all of this. I'm going to square all of the factors separately. And then we look at this expression and this expression, and we ask ourselves what they have in common. They both have a rho squared sine squared phi, so we can factor that out. And then we ask ourselves, this times what would give us this, and what's missing is the cosine squared. And then we add, well, this times what would give us this, that's the sine squared. Isn't that nice? Sine squared plus cosine squared, same angle, so that's going to be 1. And now we have rho squared sine squared phi equals 4. Now, a couple of things that we should note. Rho is positive, so we can take the square root of both sides and we can just take the positive square root. We don't have to say plus or minus a number here because rho is positive. Another thing we should note is that sine of phi, well, if phi is between pi over 6 and pi over 2, remember what your sine function looks like. It looks like this. All of those values on the sine graph are positive values. So this is positive and this is positive. So when we take the square root, we don't really need a plus or minus. We can take the square root of both sides and we get this. Square root of 4 is 2. If I want to get rho by itself, I can divide by sine of phi. And of course, dividing by sine of phi is the same as multiplying by cosecant of phi, because 1 over sine is the same as cosecant. So those are our bounds. That is our upper bound for rho. Now we've got our bounds for rho, theta, and phi. Okay. Now we just need the integrand here. And basically the way that works is we need to find the original integrand in terms of the new variables, and then we need the volume piece in terms of the new variables. Well, in spherical coordinates, volume is rho squared sine of phi times d rho d phi d theta. And that comes from the Jacobian. And then f, which is the square root of x squared plus y squared, can be written in terms of rho, theta, and phi in the following way. Well, remember, x squared plus y squared is something we've already simplified. This was x squared plus y squared. So that simplifies to this, which simplifies to this, which simplifies to this. So x squared plus y squared is actually this. It's rho squared sine squared phi. And again, because those functions are, or those variables, the variable itself here and then the function over here are positive over our region, we can just take the positive square root of all of that and we get f equals rho sine of phi. So we've got rho sine of phi times dv, which is rho squared sine of phi, d rho, d phi, d theta, and rho goes from 0 to 2 cosecant of phi, and phi goes from pi over 6 to pi over 2, because we're starting at that cone and going to the xy plane, and theta goes from 0 to pi over 2. And then these guys can be combined, simplified, that's our new integrand. Got 3 rows, so that's rho cubed, and a sine of phi times a sine of phi is a sine squared phi. And that's for the second integral. The rho cubed sine squared phi here. The only thing that would change for the first integral is the bounds. The integrand stays exactly the same because it's just that f written in terms of the new variables times the dv. So this will also be rho squared sine squared phi. Okay, so now we've got 2 options for evaluating these integrals. Actually did this last night, but it was taking so long that I quit. This first integral takes a really long time. And it's not that difficult. You might think, oh, that's 1 integral and that's 2 integrals. That'll be faster than this. But the challenge with this is that after you integrate with respect to z, you're going to have r squared times z, and you'll evaluate from 0 to the square root of 16 minus r squared. After you use a fundamental theorem of calculus, you're going to end up with r squared times the square root of 16 minus r squared, which can be solved with integration by parts if you're clever about the way you split up those pieces. And after you do the integration by parts, one of the integrals will require trigonometric substitution. When I tried to follow that path and explain every step as I do when I make these videos, it took a really long time. And we ended up with a cosine of 4 theta and a sine of 4 theta and a sine of 2 theta. And we had to use a bunch of trig identities. And it was just going to be a really involved process. So even though this integral is just 1 integral and this one is 2, I think the integration is actually going to be easier over here. So let's evaluate the integrals in spherical coordinates and see what we get. And we'll just do the first one first. We've got the integral from 0 to pi over 2, of the integral from 0 to pi over 6, of the integral from 0 to 4, nice constant bounds. It's going to make it nice and easy. Of this. And remember how this works. You start on the inside and you work your way out. So we do this first. Now, when we're anti-differentiating with respect to rho, we're treating phi as a constant. So if you want, you don't have to do this, but if you want to, you can factor out that sine squared of phi and think of that as a constant now, times the integral from 0 to 4 of rho cubed d rho. Okay, that's an easy integral. Just use the power rule, add 1 to the exponent, divide by the new exponent, then we evaluate from rho equals 0 to rho equals 4 by the fundamental theorem of calculus. So what we end up with is 4 to the 4th divided by 4, so it's going to be 4 cubed, or 64, minus this expression evaluated at rho equals 0, which is, of course, 0. So that's nice. We got a constant factor of 64 here. We can factor that out from everything, and then we'll evaluate the integral with respect to phi next. I like this much better than the other one. I tried the other one last night because it was only one integral rather than two. And I thought one integral is better than two integrals, but it's just going to be a lot of trig sub and trig integrals and a review of trig identities. And I don't mind that. I actually really like that, but I don't think everybody does. So we'll do this instead. All right. So now we'll evaluate this integral next. I've got sine to an even power. Our trigonometric integrals techniques tell us that if we have sine to an even power, we should use our power reducing formula. This is the same as 1/2 of 1 minus cosine of double the angle. I don't have a basic rule for that, but I do have a rule for that. So we'll factor out the 1/2. 1/2 of 64 is 32. And now we'll just evaluate this innermost integral. Easy breezy. The antiderivative of 1 with respect to phi is phi. The antiderivative of cosine is sine. If it was just an angle, then we would just put the angle in. But instead, we've got 2 times that angle. If I'm taking the derivative of something that looks like this, I would have to multiply by an extra 2 by the chain rule. Since we're taking the antiderivative, we divide by 2. So that's the antiderivative. And then we evaluate from phi equals 0 to phi equals pi over 6. So we have 32 times the integral from pi over 2, or 0 to pi over 2 of this, pi over 6 minus 1/2 of sine of pi over 6 times 2, minus 0 minus 1/2 of sine of 0. Of course, sine of 0 is 0, so we're just subtracting 0, which doesn't do much. 2 times pi over 6 is pi over 3. Remember, pi over 3 is a 60-degree angle. The sine of that, well, I can figure out the sine of a 60-degree angle by drawing a triangle. This is a 30, 60, 90 triangle. Opposite the 30 has a side length 1. Opposite the 60 has a side length square root of 3. Opposite the 90 is 2. Obviously, this is not to scale. But sine of that angle is opposite over hypotenuse. So this is going to be square root of 3 over 2. So we've got square root of 3 over 2 times 1/2 times pi over 6 times 32. And if I multiply those fractions together, multiply straight across, you've got square root of 3 over 4 there. And I'm just pulling that constant out. Then I'll have a 1 left inside. The antiderivative of 1 is, of course, just your variable. In this case, our variable is theta, and we integrate from theta equals 0 to theta equals pi over 2, just using the fundamental theorem. So we're going to have pi over 2 minus 0, which is, of course, just pi over 2. And if you want, you could call that 32 pi over 2, and this is pi over 6 minus square root of 4 over, or square root of 3 over 4, and 32 divided by 2 is 16. So if you want, you could call that 16 pi times pi over 6 minus square root of 3 over 4. And if you want, you could distribute and see if that simplifies at all. It does a little. It's 16 pi squared over 6 minus 16 pi times the square root of 3 over 4. 4 goes into 16 4 times. 2 goes into 6 3 times, and 2 goes into 16 8 times. So we end up with 8 pi squared over 3 minus 4 times pi times the square root of 3. It's a lot. Excuse me. Now, I know that it's a little arithmetic at the end. That was just our first integral. That's the first part. Now we have to evaluate the second part, which is a little trickier because we've got a bound. It's not just a constant this time, but it's really not too bad because cosecant and sine are reciprocals of each other, and there will be some cancellations. All right, so remember, this is your result for the first integral. Now we're going to evaluate the second integral. And it's the same as before. We just start on the inside and work our way out. And we can say that if we're integrating with respect to rho, that this sine squared phi is a constant, so you can factor that out. And then we'll multiply by the antiderivative of rho cubed with respect to rho. So just use the power rule. Add 1 to the exponent, gives me rho to the 4th, and then divide by the new exponent. And then we evaluate from rho equals 0 to rho equals 2 times the cosecant of phi. Okay, so let's see what happens here. When we evaluate this at rho equals 0, we're just going to get 0. So we're going to subtract 0 from something. It's not going to do anything. But when we evaluate this at rho equals 2 cosine of phi, let's see what happens. I said cosine, I meant cosecant, sorry. Well, we've got some simplification to do. I've got a product raised to the 4th, so I can apply that 4th power to the 2 and the cosecant. So we have the integral from 0 to pi over 2 of the integral from pi over 6 to pi over 2. So I'm really ignoring that and just sort of writing it down for later. Now remember what we're doing. We've got 2 raised to the 4th power. So it's 2 times 2 times 2 times 2. So that's 4 times 4. And 4 times 4 we know to be 16. Okay, so we'll have 16. And then this cosecant of phi is raised to the 4th as well. So we have that. And of course, 1/4 of 16 is 4. Okay. Now I can bring that 4 outside. And I just want to remind you of a fact from trig. Remember, sine of an angle is 1 over cosecant of the angle, and vice versa. Cosecant of an angle is 1 over sine of that angle. So if I have this cosecant to the 4th, I can write 2 of those as 1 over sine squared. So that's cosecant squared there, times an extra cosecant squared phi. You could have written them all that way. You could have written that as 1 over sine to the 4th and then canceled 2 of them. But I wrote it like this so that we just see the ones that cancel, and then we still have that cosecant squared phi. And that's pretty nice. I don't actually have a rule for cosecant squared, but I do have a rule for cotangent squared. And remember this fact from trig. We know that 1 plus cosecant squared of an angle is cotangent squared. Oh, whoops, that's backwards, sorry. 1 plus cotangent squared of an angle is equal to cosecant squared of the same angle. And actually, the one I have a rule for is cosecant squared. Very good. Got a little bit mixed up for a second there. I was thinking about writing it in terms of this, but actually if I was over here, I'd want to write it in terms of that. So this is not necessary this time. Sorry about that. I think I've had too much caffeine today. I think that's the problem. Let's see, now we've got that. So you might say, okay, what do I take the derivative of to get something that looks like a cosecant squared? Well, the derivative of cotangent of an angle is negative cosecant of an angle. So that means the antiderivative, or negative cosecant squared, that means the antiderivative of cosecant squared must be negative cotangent of that angle. And we'll evaluate that from that angle going from from pi over 6 to pi over 2. I'm factoring that out because that's all constant with respect to theta. And then I have the rest of my integral over here. It's the integral from 0 to pi over 2 of 1 with respect to theta. Oh, I skipped a step. Normally we would do this first and then pull the factor out. You can do it in this order instead. You're going to get the same result. So I have negative cotangent of pi over 2 minus a negative cotangent of pi over 6. We'll do the trig in just a moment. The antiderivative of 1 with respect to theta is theta. We evaluate from theta equals 0 to theta equals pi over 2. And that's just going to give us a pi over 2. So you have 4 times pi over 2 times this expression over here. And 2 goes into 4 twice. Okay, cotangent of pi over 2. Well, remember that's cosine of pi over 2 divided by sine of pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So cotangent is 0 there. Because our cosine graph looks like this. And the first time it's 0 on the interval from 0 to infinity is at pi over 2. So you have 0 divided by 1, in this case, times negative 1, which is, of course, still 0. And then for this one, I'm thinking of a triangle. Pi over 6 is a 60-degree angle. Sorry, not a 60-degree angle, a 30-degree angle. I had way too much caffeine at lunch. Pi is 180 degrees. If I take that and I divide by 6, I'm going to get 30 degrees. So the question becomes, well, what's the cotangent of a 30-degree angle? Well, that makes this a 30, 60, 90 triangle. Opposite the 90 is a 2. Opposite the 60 is a square root of 3. Opposite the 30 is a 1. Cotangent is adjacent, or adjacent over opposite. So we get square root of 3 over 1, or just square root of 3. So we have 2 pi times the square root of 3 here. Okay, that was a lot. That was our second integral. So we're taking 2 pi times the square root of 3, and we're adding it to this quantity. So the original triple integral is this. It's 8 pi squared over 3 minus 4 pi times the square root of 3 plus 2 pi times the square root of 3. Negative 4 plus 2 is just negative 2. So we're going to have negative 2 pi times the square root of 3. Okay, so that is our answer. Took a little bit of time, that's okay. We don't mind because we like calculus. I think it's fun. And the way we did that was we chose to evaluate this integral and evaluate this integral and add them together. Again, you could have chosen to evaluate this one instead. And that was my initial choice last night when I tried to work this problem. I thought evaluating one integral is better than evaluating two integrals. But the trigonometric substitution got to be so complicated and it required so many different trig identities that I thought from the student perspective, you'd probably rather evaluate these. So let me know if you want to evaluate this. We can do a little trig sub review if you want to. We can do that together. But it's not necessary. Even though this looks like more work, the work involved is actually a little easier and probably a little bit easier to access from your short-term memory. Or not short-term memory, long-term memory. Gosh, too much caffeine today, for sure. So yeah, that is how that is why I would choose to evaluate this as opposed to evaluating that. But either way, you would get the same answer. That is the value of this triple integral right here.